Hello everybody, my name is Nurla, and today I'll be talking about our paper, SGXonerated, Finding and Partially Fixing Privacy Flaws in TE-based smart contract platforms without breaking the TE. And this is joint work between myself, Yuchi Lee, Yan Ji, Jasleen Malvi, Tom Urich, Sylvain Belmar, and Professor Andrew Miller. And we all come from some combination of the University of Illinois Urbana-Champaign, Cornell University, the Initiative for Cryptocurrencies and Contracts, and Decentralized Systems Lab. So when we look at blockchains today, we can typically think of three different components. Transactions are submitted to a transaction pool. Transaction simulation occurs when we execute the associated smart contract code. And our transactions are ordered into blocks before they are submitted to the blockchain node. Private blockchains also have these same three components, except now your transaction pool is encrypted, your transaction execution is private, and you are now ordering transactions without knowing their contents. Trusted execution environments is one way of implementing privacy for blockchain networks. These TEs have hardware-based guarantees for code execution. This includes hardware isolation, which ensures your privacy because not even the host operating system can view the code execution or memory inside the TE. And it provides integrity because the host operating system cannot tamper with the code once it is inside the TE. And with the use of remote attestation, we can create a proof that we are running genuine hardware and what code is running in that hardware. And we can also send this proof to remote parties, such as the other network participants, for verification. So Secret Network is one such blockchain that uses TEs for privacy. So the applications built on this network demonstrate the great possibilities that adding privacy can unlock for blockchains. But unfortunately, they take for granted the fact that the TEs that we use today still have some limitations. So even if the TE works perfectly with no manufacturing bugs or leakages through side channels, they still have some limitations. And as a result of this oversight, our simulation attacks and access pattern attacks work even if the guarantees of the TE are maintained. One such limitation of the TE is that only things inside of the TE are hidden. So the untrusted host can actually see the interaction between the TE and the outside world. And they can see things such as the inputs being loaded into the TE and the outputs being returned from the TE. This means that during our smart contract execution, they're allowed to see certain side effects, such as if a transaction succeeds or fails. Another limitation of the TE is that it relies on inputs coming from the untrusted host. So therefore, the outputs can only be counted as trusted if there is a reliable way to validate these untrusted inputs inside the TE. Unfortunately, Secret Network does not uphold this principle because before a block is finalized and accepted by the network, they allow the miner to arbitrarily order transactions and insert their own malicious transactions. This has the potential to corrupt the untrusted database states and therefore force the victim transactions to execute against an arbitrary state of the attacker's choosing. In order to demonstrate how critical these mistakes are, we will look at a concrete example of how this can go wrong. So this is going to involve fungible tokens, which are a currency that is traded on blockchain networks. So on transparent blockchain networks, all of the transaction details involving these tokens are public. But on Secret Network, they have these privacy tokens that add privacy guarantees to your transactions. So the goal of these privacy tokens is to hide the account balances of the sender and receiver, as well as the amount being transferred and the receiver's address. And importantly, the sender's address remains public because the sender is required to pay the transaction fees to the network. So we are able to break all of the privacy guarantees for these privacy tokens, but I'll just start with showing you how you can get any user's balance amount. So first off, we start with the victim's balance being encrypted on the untrusted host. The attacker sends a malicious transaction that sends a known probe amount P to this victim. If this transaction succeeds, the attacker doesn't learn anything about the victim's account balance. It's important to note that although we're doing the simulation of sending money to the victim, we don't actually send the money because the miner isn't required to actually send this transaction to a blockchain. So they continue sending these malicious transactions, but every time they would slightly increase the probe amount P. And finally, when this transaction fails, it will be because of this overflow error. So when this overflow occurs, the attacker now knows that the victim's account has this max unsigned int value subtracted by that probe amount that caused the overflow. And so now we are basically able to infer the victim's supposedly private account balance. This principle allows us to do a couple other attacks where we learn other private information about the user's transaction, such as how much they are sending in a transaction. So how can we actually validate these untrusted transactions to ensure that they're not malicious? So the key idea here is to lock in the ordering of the transactions before execution. The TE should require a proof of publication to verify that the transaction ordering is finalized before they do any execution of the transactions. So this proof of publication involves validating that this new block has indeed been accepted by the network, and this validation occurs inside the TE. So as a result of this work, Secret Network has implemented this mitigation. Next, I'll look at how we can use similar principles to enable access pattern attacks that allow us to reveal the receiver of a token transfer. So when we do a token transfer, we have to somehow update the recipient's balance. So this involves fetching the user's current balance from the account database on the untrusted host. This GET request uses an encrypted key associated with the user's account. But although this key is encrypted, the same key is used across every database access of this account balance. So remember that in Secret Network, the receiver of the transaction is hidden, but the sender remains public because they pay the transaction fees. So we can therefore look through past transactions and figure out which encrypted key is associated with that user based on previous transactions where they sent some tokens. So we can use this correlation to figure out some connection between the recipient's address and this encrypted key, and we can link this encrypted key to the load that occurs when we are updating the receiver's balance. So the known way to mitigate access pattern leakage is through this data structure called oblivious RAM or ORAM. So in ORAM, every time we do a read or write access, we actually update the location of this piece of data that we have read or written. So this actually adds a bunch of overhead to storage accesses because now, even if we're just reading a value, we have to update the data structure. And this cost is particularly problematic in the blockchain space because this kind of storage access updates must be replicated across all nodes in the network. And so now users have to create a transaction and pay transaction fees simply to read their account balances. So the Secret Network has opted to implement a simpler and cheaper mitigation strategy by reading a number of decoy balances in addition to the user's balance. So this only provides some limited anonymity as the attacker can kind of guess which decoy is the victim's based on maybe previous transactions if it is a frequently used account. And this can be done with some static probability because you're loading on the same number of decoys across the different transactions. Attackers can also opt to create new accounts for relatively cheap that can be one of the randomly selected decoys. So this is a way that the attacker can increase their chances of guessing the real receiver, because they can kind of eliminate some of the decoys as being not from the victim. This also creates some misaligned incentives, because now the sender is responsible for picking the number of decoys, which also increases the sender's transaction fees, and now the sender is responsible for the receiver's privacy. So in the full paper, we have gone into detail about other attacks, including figuring out the transaction amounts and how you can extract some profit by using this private information. And we have also gone into detail about other smart contract platforms that also use TVs. Thank you.
Thank you so much, Nana. And also this paper is articles reproduced, so that's a nice thing. Any questions?
So the problem with identifying the recipient of the money is the fact that you've got the same key each time. Is there a way of rotating the keys, or always moving the money to a new account each time, or some other way of avoiding that repetition?
Yeah, that's basically what the ORAM data structure is doing, because like you're basically just changing the location of the account every time. So it's basically perfectly hiding which account you're accessing.
So it's not the cheaper way of doing it.
Yeah.
So you mentioned that the ORAM implementation costs significant overhead for your system. So did you actually implement the ORAM implementation and compare it with your approximation or sort of alternative strategy that you were describing?
Yeah, so we actually did come up with a way to have this ORAM data structure be used by like not every node in the network, just have a single node that implement the ORAM and like post the results on chain. But this kind of added a lot of complexity to their system, so they didn't really want to implement it.
And so does that also increase the traffic going to a single node, because now that one node is responsible for doing all the shuffling of the data across the address spaces, correct?
Yeah, exactly. You can choose to like, choose different nodes each time, like do some load balancing, but like, yeah, it's a major like change in the trust assumptions of the system to like only have it be on one node versus every node.
I see. Thank you.
Quick question from me, if you don't mind. So the first attack discovering the account balance, would that attack be detectable by the victim?
No, it wouldn't, because it all happens like before any block is submitted. Like the victim has no idea.
So much, Anna.
It's a very quick one. So I understand why you reveal the sender, so that you can audit the fact that there are no double spends, right?
Mm-hmm.
But then you cannot audit that a bad TE, for instance, would create money out of thin air by giving to the recipient more than the money that it should be allowed, right?
So that's not actually possible, because the computation is the real computation that is like in the blocks is replicated on every node in the network. So even if one node is like doing something sketchy, like the other nodes won't accept that.
Okay, so the threat model is not a full audit. So you abandon the idea of full nodes that would not trust the execution and rerun a full audit. It's just pure state machine replication that you have there.
Yeah.
Cool.